Okay, so hello students. So today we will do a very interesting problem of quantum mechanics, and it has been asked in the previous year NET JRF 2022. So what's the question? You can see the question on your screen. So the question is very simple and straightforward, that a potential is defined like this. This is a kind of semi-infinite potential. Here you can see at x is equals to 0 and less than 0, potential is infinite, and in between 0 to a, this potential is minus v naught, and greater than a, this potential is 0. So this is the potential, and we need to calculate the relationship between energy and potential for the bound state of particle, right? We need to calculate the bound state for the particle in this kind of potential. So let's first draw the potential, then we will see that how we can find out the bound state. So you see, if you draw this potential, it's very simple, one-dimensional problem. I can draw this potential. Let's suppose this is x direction and this is potential Vx. Now see, at x is equals to 0 and less than 0, in this complete region, potential is infinite. Also from 0 to a, the potential is minus v naught. So I can say, let's suppose this is x is equals to 0. In this region, potential is, I can define it like this. Here you can define minus v naught. This is from 0 to a, and greater than a, in this region, this potential is again 0. So we have this kind of semi-infinite potential. At x is equals to 0, it is infinite, and at x is equals to a, it has some finite value minus v naught, right? Now see, first see in what condition it will be in the bound state. Here you can see, can I say that if potential is in between this region, inside this box, let's suppose this is the particle of mass m and energy E. Particle of mass m and energy E. If particle is in between this region, minus v naught to 0, then only we can say that this is in the bound state. Because if you see, if I put the energy of particle somewhere here, let's suppose this is the level of energy. In that case, you see, it is unbounded from this side. So energy of particle must be in this bit, in this region, from minus v naught to 0. So for the bound state, can I say one thing, that energy of particle must be in between from minus v naught to 0 for bound state. This is one thing, right? Now see, we have three different regions here. Region 1, I can say, let's suppose this is region 1, this is region 2, and this is region 3. Why these are the three different regions? Because in every region, potential energy is different. So of course, in all the three regions, the solution of Schrodinger equation will be different. That means we'll find out the different wave function in all these three regions. So let's try to find out those wave function in all those three regions. Now see, very simple, you can easily write down the Schrodinger equation for every region and you can easily solve that Schrodinger equation. I'm directly writing the wave function because you know these kind of solutions. You see, in the region 1, potential is infinite. So because of the infinite potential, this particle cannot tunnel into this region. So of course, its wave function is always 0. You know this kind of solution. So can I say, in region 1, the wave function phi x is 0. Agree? Now see, what will happen in region 2? You see, region 2 is just like a 1D box. Inside that box, particle is free. It is freely moving inside this box. So its solution is the solution of free particle, plane wave solution. So I can directly write down, we know the solutions. In region 2, I can say the wave function is phi to x is a e to the power, let's suppose, iota kx plus b to the power minus iota kx, where you can define this k. This k is under root 2m or h cut square e plus v naught, because in this region too you have minus v naught potential, so you have to put that potential also in the Schrodinger equation. You will find out the value of k also. Now see, let's suppose this is equation 1, let's suppose this is equation 2. Now see what will be the wave function in region 3. Think about it. In region 3, can I say in region 3 wave function is, let's suppose, c to the power minus gamma x, where gamma is under root 2m over h cut square, energy is minus E. Why we have taken this exponential decaying function? You see, in this region 3rd, we have a finite potential at this point. This particle can tunnel into this region. You know, step potential, you have studied the step potential. If there is a potential, step potential of height v naught, and if particle is interacting with this potential, free particle, then it always decay from this potential barrier. This is the tunneling probability. Because of the tunneling, e to the power minus gamma x kind of thing. Why it is minus sign? Because the wave function must be converging. And if it is moving in opposite direction, in this direction, this will be e to the power plus gamma x. Fine. So same kind of thing is the particle, and it is interacting with this potential at this point. So because of the tunneling, its wave function is like this. Fine. So let me just remove this. Now see, here we will use a very important property of wave function. You know, the wave function of any particle must be continuous, irrespective of any regions. Wave function always continuous, right? So we will use the continuity of wave function here. So you see, if I am saying, I am making this statement that wave function must be continuous. So it must be continuous in region 1, it must be continuous in region 2, it must be continuous in region 3, right? So can I say at x is equals to 0 and at x is equals to a, the wave function must be continuous. Now at what condition it will be continuous? At x is equals to 0. How you will identify that it is continuous at x is equals to 0? So there is only one possibility, then when the wave function in region 1 and wave function in region 2 is equal at x is equals to 0. When these two wave functions are equal, then only I can say that at x is equal to 0 it is continuous. Similarly at x is equal to a I can say, right? So I will use the continuity of wave function. Since wave function must be continuous, just use the continuity. Now see, use the boundary condition at x is equals to 0. So at x is equals to 0, can I say phi 2 at x is equals to 0 must be equals to phi 1 at x is equals to 0? Phi 2 and phi 1. Now what is phi 2? I can say, if you put in equation 2 x is equals to 0, so you will get a plus b, and this is already 0, 0. So from here I can say that b is equals to minus a. Let's put in equation 2. Put this in equation 2, so I can get phi 2x is, I can take a common, e to the power iota kx minus e to the power minus iota kx. Right? Now what can I do? Just multiply by 2 iota and divided by 2 iota. So this will become, you see, a into 2 iota. This is another constant. Let's suppose this is some another constant d. And this e to the power iota kx minus e to the power minus iota kx divided by 2 iota. This is simply sine kx. Let's suppose this is equation 4. Now you see. Now we will use the boundary condition at x is equals to a. So again I can say at x is equals to a, I can say the wave function phi 2 at x is equals to a must be equals to phi 3 at x is equals to a. Now to put the value of a in phi 2 and phi 3, let's put. So if you put, so this will become a, sorry, not this one, I can use now this one. Now you can use this wave function d. So this is d sine k is equals to, this will become now, from this equation I can say c to the power minus gamma a, and let's suppose this is equation 5. Fine. So we have used the continuity of wave function at x is equals to 0 and x is equals to a. There is one more property of wave function, that its first order derivative must be continuous, right? Because then only you can define the energy operator. If first order is continuous, then only you can define the second order derivative, right? And you see in the Schrodinger equation there is a second order derivative. So that is possible only when first order derivative is continuous. So again we will use that property, that first order derivative of wave function must be continuous at x is equals to 0 and x is equals to a. So I will use at x is equals to a. So I can say, again I can say that d phi 2 by dx at x is equals to a must be equals to d phi 3 by dx at x is equals to a. Let's use this one. So I can differentiate this equation. So this will become dk cos ka, and this is equals to, if you can differentiate this equation, minus gamma c e to the power minus gamma a. Let's suppose equation 6. Fine. Now see what we will do. We can use this reason now. Now see, can I divide equation 6 by 5? Equation 6 by 5. So what you will get? dk cos ka divided by d sin ka, and this must be equals to minus gamma c e to the power minus gamma a divided by c e to the power minus gamma a. Fine. Now you can cancel. In this one d and d you can cancel, so you will get simply cot ka, and from this side you will get, you can cancel these two terms, and this is minus gamma, and this k is also there. So further I can say, let's suppose this is k square, do the square of this one, this is cot square ka, and this is gamma square. So this will give you cot square ka is gamma square divided by k square. Now you can put the values of k and gamma. So this will become cot square ka, and gamma is 2m minus e divided by h cut square, and this is divided by 2m over h cut square e plus v naught. These two terms we can cancel. So this will become, you see, cot square, and this k you can also put. So this k is nothing but a, I can put as it is, and this is under root 2m e plus v naught divided by h cut square, and this is equals to minus e over E plus B naught. This is the solution. This is the final answer. So in the options you will get this answer. So see, here you can see the direct relation between energy and potential. It means when particle will satisfy this equation, then only it will be in the bound state, right? So it's a very straightforward question. The thing is, you have to understand the sequence and you have to understand the problem, that how to deal with this problem. This approach is very interesting. Fine. So this is how we can do this kind of solutions. Fine. So if you like the discussion, just write down in the comment section. And if you need any other solutions related to the physics, any quantum physics, classical physics or other subjects, just write down in the comment section. Okay. See you in the next video. Thank you.